In this lab, we imagine a scenario of which a star is orbiting a black hole of an unknown mass. The direct purpose of this lab was to observe the motion of the star via a computational model and use that to calculate the mass of the black hole. Broadly speaking, the other goal of this lab was to show how actual physics phenomena can be explained and solved by fundamental physics principles. The results of this lab estimated that the mass of the black hole to be 5.51 e to the 31st. This is an enormous value. It's almost 28 times bigger than the Sun. The fundamental laws of this experiment are Newton's universal gravitational law, where F_net is equal to g times m1 times m2 over r squared, where g is the universal gravitational constant, m1 is the mass of the star, m2 is the mass of the black hole, and r is the magnitude of the position vector of the star. Using this equation, we can rearrange it to find m2, or mass of the black hole. The equation is given here. The result of this experiment is Newton's second law, or the momentum principle in our case. Breaking down the momentum principle into its derivative form, it is given as F_net is equal to dp over dt. This equation shows that the change in momentum is equal to the net force acting on the object multiplied by the duration of the interaction, at least in interactions where change in time is very small, as in our case here. Now that we have some background for our lab, we can get to our computational model and calculations. The experimental setup is that a star of 4.7983 e to the 27 kilograms is orbiting a black hole, which is located at -5 e to the 10th, -3 e to the 10th, 0 meters. The change in time is approximately 1 day. Here I've given you my lines of code. Underneath my bullet points, I've given you my lines of code in which I entered this data into Python. In our while loop, which we've seen in previous labs as being very important for their iterative function, we can see the first lines used for calculating initial and final velocity. We can use this initial and final velocity to find the initial momentum and the final momentum by multiplying mass by velocity. Then, we can subtract the final momentum by initial momentum to get the change in momentum. Now that we have delta p, divided by delta t to get dp over dt. Remember earlier from the momentum principle that F_net is equal to dp over dt. Now F_net is composed of two components, F_net parallel and F_net perpendicular. Finally, let's calculate our forces. Finding the direction of momentum by using initial momentum over magnitude of initial momentum. We can then find the parallel component of F_net because it is equal to dp dt parallel, and then F_net perpendicular because it is equal to dp dt perpendicular via the momentum principle. You can pause the video here to have a closer look at the equations. Remember how we rearranged Newton's law of gravitation to find mass of the black hole? It is given by this line of code. The other values such as F_net, g, and mass of the star are known, but the r squared value is given by a star position minus black position squared. Python will then print us out the value of the mass of the black hole, rather than making us calculate. Let's run our module. The blue arrow is the perpendicular net force, yellow parallel net force, and black arrow is total net force. The arrows get larger as the star, the one on the curved path, approaches the actual position of the black hole, so large that Python shrinks the whole diagram for a few steps, which is why the line and the dot seem to disappear for a brief moment in the model. The reason the arrows get huge and shrink the model is because when the star gets closer to the black hole, r in the universal law of gravitation, star position minus black hole position, is smaller, and this makes F_net on the whole larger. In this setup, we assume that F_net on the star is only due to the gravitational force. This is where the mass of the black hole is printed out. Because all these numbers differ slightly, rather than taking the final mass as total mass, I averaged all the estimated values together to get a more accurate mass, 5.51 e to the 31st. How is F_net and F_net parallel and perpendicular different from momentum? We did say that F_net equals dp over dt equal to delta p over delta t, and we did say that F_net parallel is equal to dp dt parallel, and F_net perpendicular is equal to dp dt perpendicular. How are they different? Fundamentally, they describe different things. F_net is all the forces acting upon an object. These forces cause motion. dp dt is calculated by change in velocity over time. It is an observation of motion. To simply put it, Fnet causes motion, and dp dt is the result of these forces. Even though numerically they may be the same, they describe different things. One last question of the day. Is it possible for you to find a value for the mass of the new black hole that is different from the mass you found in the original one? No, because we assume that Fnet is equal to F gravity. If we have a new motion, then this must mean the black hole has a new mass. A new mass would cause a different F gravity, which then means a new Fnet, which then would make a new motion. If we have the same motion, we should have the same mass.